this lab practice number 4, we're gonna see the topics about cementation, quenching, and tempering. For this lab practice, our main objectives are two. The first one is to apply the principles of solid state diffusion to cement carbon steel rods in order to increase the mechanical properties of the outer layer of the part that we're going to be using, and to provide adequate tenacity in the core of the part. And the second objective is to analyze the effects of cementation variables on the results obtained. For this lab practice number 4, we used different materials. Our first material was the steel 1045. That was the one that was selected for our team. And also, as equipment, we used the protective equipment because we were exposing to high temperatures, because we were using the muffle oven that it has a temperature up to 950 degrees Celsius. Also, we used the Beaker's machine in order to calculate its hardness, and also the equipment for the metallography preparation. Also, we use the safety shoes in order to maintain order and to be safety. And finally, we use the iron, the tweezers for the iron box, and also the iron box that was important with the lid in order to make our lab practice.
For this lab practice, what we did was we took our 3 pieces, we put them in our box with our carbon and our other additives, and what we did was we put them first for 12 hours at 900 degrees Celsius. We put the 3 pieces of 1045 steel that we had. Then, after we took them out, we quenched them in cold water. Then we put only 2 of the 3 pieces, piece 2 and piece 3, in the oven for 15 minutes at 800 degrees. And after that, we quenched them again. And finally, we just put 1 piece, piece number 3, in the oven at 200 degrees for 15 minutes.
And now we have different topics that is really important to know, because it's the base of our procedure. First of all, one important topic is the carburizing. It's the first step that we did to do the cementation. It's a method that we know, and it's really easy to do it. The carburizing, you have a box, a metal box that it could name hardcover. Then we fill it with carbon dust, and then we add additives to help our procedure happen the reaction. We add sodium, calcium, and barium carbonate. Then we put our 3 pieces. We fill out all the box, and then we seal it. Then we introduce into the furnace and wait till the reaction happen. It could take different time, depending of the carbon potential of our furnace. This is really important to know, because the carburizing basically it's really important because we will give to our material different properties because of the diffusion of the carbon by atomic diffusion. We'll give to our material a cemented layer. This is for material that it's in contact and it's really easy to failure by impact. So we are going to give to our material a hard layer in the surface and a ductile or soft core. This is for what I mentioned, to reduce the failure for impact. Then we have the carbon potential that of atmosphere. This is the coefficient that our furnace or oven will give to us of how much quantity of carbon will impact to our material. Then we have the carbon equivalent, that is the amount of carbon that our material gain or have.
Well, I'm going to explain what is cementite. Cementite is the uses of carbon on steels with low percentage of carbon in it. And there are 3 types: solid, gas, and liquid. In the solid, we use a steel box where we use carbon gas, then we do the heat treatment. Then the gas cementite is the most efficient one, where we use propane to obtain all the carbon gases to be able to create this cementite. And the liquid cementite is one of the best uses in the industry, where we use molten salt and then preheat it and then putting it in a molten bath. The quench process is when you cool a material that has been having a heat treatment before. So in our this practice, we put these 3 pieces at 900 degrees, 800 degrees, and 200 degrees. And each time that we take it out, we do quench, putting it in water in the 3 cases. So this will be the quench process during this practice. Tempering will be the heat treatment process, in which in this practice we know when we change from 900 to 800 to 200, so this will be like the tempering process during the practice.
Now I'm going to explain the depth of the layer that we obtain in our carburizing process of our material. First of all, we have this formula that is given to obtain the distance here with the X, and this is with the CS, that is the 1%, that is the carbon potential that our furnace gives us, is the atmosphere potential. The CX, that is 0.45, that is our carbon present in our material that we want to obtain. Then the CO, that is 0.1%, that is the beginning percentage. This formula will give us the error of C, and if we interpolarize, we obtain 0.6094. Then we use the formula of diffusion. This will help us to obtain the change of distance in a period of time. That's why it's centimeters square upper seconds. Then we obtain this. The temperature is 930 degrees, and we change it to Kelvin. Then we obtain we use the general value of the gas, and it's 1.987, and then the coefficient of energy that we need, that is 32,900 cal per mole. Then we use this, and the result is the 2.42 per 10 minus 7 centimeters square upper seconds. This the initial is the coefficient diffusion of the steels here present in the carburizing. Then finally we use this to calculate the error, and then we obtain X, that is 0.1017 centimeters, that is the deep of our layer in the carburizing process. Micrographic analysis. In the first piece, we obtain that we count 6 grains in a resolution of 500 amplification, and we obtain a number of 8 ASTM for our material. Then we got the second piece that we did 2 treatments. First we heated to 900 degrees, then we reheat at 800 degrees, and we count 15 grains at amplification of 500, and we obtain a number of 10 ASTM. Finally, we got the third piece that we did the 3 treatments, and we obtain 8 grains and ASTM of 8. We want to remember that if the ASTM is bigger, we got better properties, like and we can see it in the bigger test, because we obtain this 10 in ASTM number, and in the bigger test we got higher results in the hardness test. So we can conclude that these have better properties, and well, these we can see that have the worst properties in the 3 of the pieces. In the application of cemented steel, it's very useful because we want in some products, in some parts, we want that our material doesn't fail by impact. So we found few examples like blades. Blades, it's a very important part in many products, many machines, like in grass cutting machine. It's important that doesn't break because of the impact, doesn't fail because of the impact, and we want the blade doesn't lose the sharpness of the part. Also in axes, we want to maintain the sharp in the axe, and we submit the axe to impact a lot of times. So we want to resist our axe and thus don't lose the sharpness. Then we have shaft gears. Shaft gears is a really important part in a transmission. They are in constant impact, so we want, like in this diagram, we want in our gear, we want like soft core and a hard surface. This to resist, as I mentioned before, we want to resist the impact and doesn't fail. Also, it's important to mention that in impact tools and in part tools in general, it's important this type of process. Actually it's not used, it's not commonly used, but because there are other processes that are more efficient and less cost to the industry. So that's why this is a process that we can use in this example.
For the results of the faces of our three pieces, as we can see in the diagram, when we heat up to 900 degrees, we have 100% austenite. And after the 12 hours that we left them in the oven, and then when we took them out and we quenched them, they became, because of the water quenching that we did, they became a phase that was a mixture of austenite and ferrite. Then we grabbed the pieces and we put them into the furnace again at 800 degrees, and when they were at 800 degrees they became again 100% austenite, and all the information that was embedded in them went away. Then we quenched them again with water, so that made them become again ferrite with austenite. And then only to one of them we applied a heat treatment, which was we put it in the oven at 200 degrees, which made that become martensite with unstable austenite. And when we took them out and we left them at room temperature, the martensite was still martensite, but the unstable austenite became into perlite because of the way the piece cooled down.
Finally, we did the beaker test to measure the hardness of our materials. We make sure to sand the piece well to allow us to do the test correctly from the shore to the center. We did the test 50 micrometers to the shore to the center. In the piece 1, we got in the shore 817 and it decreased to 734. In the piece 2, we got in the shore 900 and in the center 854. And in the piece 3, we got 887 and it decreased to 794. So we can conclude that the hardness in the shore, in the limit of the bakelite, it's bigger, it's greater than in the center, and that's what we want in our material. We want a surface harder than in the center to what we mentioned before, to allow the material resist to the impact. With this practice we learn a lot about heat treatments and how do they impact in our materials, can we improve the properties of our materials, like with the quenching, the temper, how do the temperature impact in the properties, do it our material harder or ductile, if we have like microconstituents that will help to determine the properties of our materials. This is a really important practice that it's really useful in the industry, because the steels and cast, in this case the steels are materials that is very used in the companies.
Conclusion for this lab practice, we can say that we learn about how to maximize the potential of the materials by using heat treatment, which is a really common method to use in the industry, and it's really important because that's the way that you can adapt your material for your use. If you want it to be more ductile, you want it to have more strength, you want it to be more hard, you can do it all with these methods. So it's crucial for the course or for the life of an engineering in the professional aspect. Also, we were able to appreciate how it works and what are the results through the hardness test of beakers, which showed us the true difference, because we can make the method and only see the steels, but in order to see the proof, we were able to use these machines, this equipment, for us to really know in deep how it works.
We can conclude after doing this practice that it is very important to know how all the thermal treatments or all the heat treatments work on specific materials. For example, there are some that are only for steel, or some that are only for aluminum, etc., etc. And in our lives as engineers, it's gonna be something that we're gonna use on a daily basis. For this reason, I believe that this practice showed us a lot, that because it's not the same just to learn it in the chalkboard, but also putting it in practice is very helpful for us to get to know the concepts better and to understand in a better way.
Well, during this practice, I learned a lot of things. Basically, how important the heat treatment is over the material and its processes, and all the different types of the cementite, how these heat treatments affect in the material, how you have to do a proper quench, a proper temper, and each of these phases, how important they are during the experimental processes. And I think this in the industry is very important, because every time you want to have different properties in the material to benefit a final result, it's always a good idea to do a heat treatment. Thank you.